Welcome to the deep dive. Today, we're going deep into the world of quantum computing. Specifically, we're going to be looking at two new chips,
Huh.
Google's Willow and Microsoft's Majorana. You've probably heard all the hype
Yeah.
about how quantum computing is going to change the world. But what does it all actually mean? And how do these new chips fit into the picture? We'll be talking about error correction that's way better than we thought possible, computational speeds that make supercomputers look slow, and we'll even touch on the strange world of topological materials. Just imagine harnessing quantum mechanics to solve problems that we thought were impossible, problems that could change your field, your life. That's what we're going to explore.
Yeah, it's a very exciting time to be involved in quantum computing. Willow and Majorana show us two different paths to building practical, large-scale quantum computers, and each one tackles those fundamental challenges in their own unique way.
Okay, so before we jump into the specifics, let's make sure everyone listening is on the same page. So what exactly is quantum computing, and why should we care?
At its heart, quantum computing uses the rules of quantum mechanics, which is like the operating system of the universe, at the smallest level. So instead of bits, which are either a 0 or a 1, quantum computers use qubits. And these qubits can be in a superposition, which means they can be 0, 1, or both at the same time. And this lets quantum computers do some calculations exponentially faster than regular computers.
That both at once thing is really hard to wrap your head around, but what does that actually mean for us in the real world? Like, what kind of problems can a quantum computer solve that a regular computer can't?
Okay, well, think about simulating how molecules interact to design new drugs or materials, or optimizing incredibly complex logistics networks. These are really complicated problems. That would take a classical computer millions or even billions of years to figure out. But quantum computers could potentially solve them much, much faster, leading to huge breakthroughs in medicine, materials, science, and lots of other fields.
So now let's talk about these new chips. Google's Willow is getting a lot of attention, especially for how well it handles a big problem: quantum error correction. Can you explain why that's so important?
One of the biggest challenges in building useful quantum computers is how sensitive they are to noise. Qubits are so incredibly fragile, and even the smallest disturbance can cause errors. So that's where quantum error correction comes in. It's a way of protecting information by spreading it out across lots of physical qubits. And what's groundbreaking about Willow is that it demonstrates below-threshold error correction.
Okay, can you explain what below threshold means and why is it so important?
Sure. It means that as Google made Willow's qubit grid bigger, the error rate actually went down. This is crucial because it means that we can keep making larger, more powerful quantum computers without being completely stopped by errors. This has been a huge problem for the field for almost 30 years, and Willow's success is a really big deal.
So with Willow, we're finally seeing a way to make quantum computers that can really scale up. That's amazing. But it's not all about error correction, is it? Willow also did a calculation that would take a supercomputer a ridiculously long time.
That's right. They used a benchmark called random circuit sampling to test Willow, which is a task that's perfect for quantum computers. And Willow completed this task in under 5 minutes, while it would take a supercomputer something like 10 septillion years, which is even longer than the age of the universe.
Wow, that's incredible. That speed difference really shows you how powerful quantum computing can be. Okay, now let's move on to Microsoft's Majorana. This chip uses a completely different type of qubit, doesn't it?
Yes, that's right. Majorana is the first quantum chip to use topological qubits, which are based on a totally different approach, compared to the superconducting transmon qubits used in Willow.
Topological qubits, I have to admit, that sounds a little intimidating. Can you explain that to our listeners? What are these qubits and why is Microsoft focusing on them?
Okay, so imagine you have a knot in a rope. No matter how you twist or bend the rope, the knot stays there. Topological qubits are similar because they store information in a way that's protected from noise. And that's because they use a special material called a topoconductor, which allows for something called topological superconductivity.
So instead of actively correcting errors like Willow does, Majorana's qubits are already protected. That sounds like a huge advantage.
Exactly. The information in Majorana's qubits is stored in something called Majorana zero modes, or MZMs for short, which are found at the ends of tiny superconducting nanowires. These MZMs are protected by something called parity, which is whether the nanowire has an even or odd number of electrons, and this makes them really stable.
Okay, so how does Microsoft actually control and read the information that's stored in these MZMs? They seem pretty well hidden.
They use a clever combination of digital switches and quantum dots, which are tiny semiconductor devices. By connecting these to the MZMs, And using a technique called microwave reflectometry, they can essentially see the nanowire's quantum state and change the information. It's a very different approach from what's used with transmon qubits.
So it seems like Willow and Majorana are both making great progress, but in very different ways. What are the key differences between these two approaches? And what are the advantages and disadvantages of each?
Willow, with its superconducting transmon qubits and active error correction, is a more developed technology. It's further along, but it needs complex error correction systems to work right. On the other hand, Majorana is still in its early stages, but it has huge potential to scale up because of how stable topological qubits are.
So it's a bit like the tortoise and the hare. Willow is the tortoise steadily moving forward, while Majorana is the hare that could potentially jump ahead in terms of scale.
That's a great way to put it. It'll be really interesting to see which approach ends up being more successful, or maybe we'll even see a hybrid approach that combines the best of both worlds.
Before we talk about potential applications, I wanted to go back to the mind-blowing speed we talked about earlier. Does that speed difference between Willow and a supercomputer tell us anything about how we understand the universe? For example, does it support the idea of parallel universes?
Well, the speed difference definitely makes you think. Some physicists believe that quantum computation might actually be using parallel universes. That would explain how quantum computers can solve problems so quickly, in a time frame that's impossible for classical computers. It's a fascinating idea, but it's just one interpretation. There are other possible explanations that don't involve parallel universes.
That is a fascinating thought. All right, so let's get practical. How could these advancements in quantum computing, specifically with Willow and Majorana, impact our lives and how we work? What real-world problems could they help us solve?
Well, the potential applications are vast, and we're really just getting started. Take drug discovery, for example. Imagine being able to simulate how molecules interact at the quantum level. This could lead to developing new drugs and therapies so much faster, potentially even targeting diseases that we can't cure right now.
That's incredible. It seems like Willow, with its advanced error correction, would be perfect for that kind of complex simulation. What about Majorana? How could its unique properties be used?
Majorana's potential for scaling up could revolutionize fields like materials science. Imagine designing new materials with specific properties, like stronger and lighter alloys for aerospace, or more efficient catalysts for industry. We might even see room temperature superconductors for energy transmission without any loss. The possibilities are really endless.
Wow, those would be some serious game changers. And what about finance? Could these quantum chips change how we manage risk and make investments?
Absolutely. Willow's speed and accuracy could completely change financial modeling. Institutions could manage risk better, develop more sophisticated investment strategies, and maybe even predict market trends more accurately.
So you're saying Wall Street might need to start hiring quantum physicists?
It's possible. And we can't forget about the impact on cryptography. As we said earlier, quantum computers are a big threat to current encryption methods. But both Willow and Majorana could also be used to create new encryption algorithms, ones that are quantum resistant. So our data would be safe even in a post-quantum world.
It's like a constant battle between those who break codes and those who make them. Now, I'm really interested in how quantum computing could affect artificial intelligence. Could Willow and Majorana lead to AI that's actually smarter than humans?
That's a question that sparks a lot of debate and imagination. Willow's speed could be amazing for training AI models much faster, leading to breakthroughs in things like natural language processing, image recognition, and robotics. And Majorana's scalability could help us create AI systems that can handle massive amounts of data and solve problems that are way too hard for even the most powerful computers we have now.
It's exciting and a little scary to think about what that could mean. But we have to ask, are there any downsides or risks to having this much computing power? What if it falls into the wrong hands?
That's a really important question. Like any powerful technology, quantum computing can be used for good or bad. One concern is that it could lead to job displacement. As quantum computers get better, they could automate jobs that are currently done by humans, which could lead to job losses in certain areas.
That's definitely something to think about. It sounds like we need to be proactive about adapting our workforce and education systems to get ready for a future powered by quantum computing.
Exactly. And of course, there are ethical implications as well. We need to be very careful about how this technology is developed and used. It's crucial to have open and honest conversations about the potential risks and to create clear guidelines and regulations to prevent misuse.
So it seems like we're at a turning point, facing a future with incredible possibilities, but also potential dangers.
That's a perfect way to put it. We need to be both cautious and excited as we move forward. guided by a sense of responsibility and a shared vision for a better future.
Okay, so we've been focusing on the potential uses, but I'm also interested in the science behind it all. Could you walk us through some of the technical details of how Willow and Majorana actually work?
Sure, let's start with Willow. It uses superconducting transmon qubits, which are tiny circuits that operate at super low temperatures, just barely above absolute zero,
So we're talking colder than space.
much colder. At these ultra-low temperatures, materials start to act in quantum mechanical ways. This lets the qubits exist in those superpositions we talked about earlier.
Okay, so we have these superconducting qubits. How does Google achieve that amazing below-threshold error correction?
It's a combination of really advanced hardware and software. On the hardware side, they've made big improvements in how the qubits are designed and built, which makes them less sensitive to noise. They've also developed new techniques for controlling and entangling the qubits really precisely. Remember, even a tiny error in these operations can mess up the whole calculation.
It sounds like a really delicate process.
It is, and on the software side, Google has come up with sophisticated algorithms that constantly check the qubits and make corrections in real time. It's like having a tiny quantum mechanic always on duty, fixing any little problems that come up.
I love that analogy.
Okay.
Okay, so now let's dive into Majorana and its topological qubits. You mentioned a material called a topoconductor. Can you tell us more about that?
Creating a topoconductor is a huge accomplishment in itself. It takes incredibly precise engineering at the atomic level. Microsoft combined a semiconductor called indium arsenide with a superconductor called aluminum to create these special nanowires that have topological superconductivity.
So it's like mixing two ingredients with completely different properties to create something brand new with unique characteristics.
That's a great way to think about it. Then these nanowires are cooled down to almost absolute zero and carefully controlled with magnetic fields to create the right conditions for topological qubits to appear.
And those topological qubits are what give Majorana its built-in air protection.
Exactly. The information is stored in those Majorana zero modes, or MZMs, which are located at the ends of the nanowires. And because of the topological nature of the material, these MZMs are incredibly stable and resistant to noise.
But how does Microsoft control and read the information stored in those MZMs?
They've developed a method using quantum dots, which are tiny semiconductor devices. By connecting these quantum dots to the MZMs and using a technique called microwave reflectometry, they can essentially see the quantum state of the nanowire and manipulate the information. It's a very clever and innovative approach.
It sounds incredibly complex, but the potential benefits, especially when it comes to scalability, are really exciting.
They are. Topological qubits could be much more stable and scalable than other types of qubits. This means that Majorana could potentially be scaled up to millions of qubits without needing those complex error correction systems that are needed for transmon qubits like the ones in Willow.
So going back to our tortoise and hare analogy, Majorana could really take off in the long run.
That's the hope. Of course, it's still very early days for topological qubit technology, and there are many challenges to overcome, but the early results look very promising.
It seems like both Google and Microsoft are pushing the limits of what's possible with quantum computing. It's going to be amazing to see how these technologies develop and what incredible discoveries they'll lead to. Before we wrap up this deep dive, I'd love to hear your thoughts on what the future holds for quantum computing. What are you most excited about, and what are some of the biggest challenges we still need to address?
Yeah, it's really hard to overstate just how much quantum computing could change things. We're talking about solving problems that are just impossible for regular computers, and that could lead to breakthroughs that affect every part of our lives.
It really is mind-blowing.
Yeah.
What areas are you personally most excited to see quantum computing change?
Well, one area with huge potential is personalized medicine. Just imagine using quantum simulations to design drugs and therapies that are specifically made for each person's unique genetic makeup. This could completely revolutionize how we treat diseases and lead to more effective treatments with fewer side effects.
That's amazing. It sounds like science fiction, but with all these advancements in quantum computing, it feels like we're getting closer and closer to making it a reality.
Exactly. And I'm also really excited about how quantum computing could accelerate the development of artificial intelligence. We could see AI that can solve really complex problems in areas like climate modeling, drug discovery, and material science, helping us tackle some of the biggest challenges we're facing.
Those are some really inspiring possibilities.
Yeah.
But you mentioned some challenges earlier. What are some of the hurdles we still need to overcome to really unlock the full potential of quantum computing?
Well, scalability is a big one. While chips like Willow and Majorana are definitely steps in the right direction, we still need to build quantum computers with millions of qubits to tackle the really complex problems. And even with all the progress in error correction, it's still a massive engineering challenge to keep those qubits stable and coherent.
So it's kind of like building a house of cards.
Yeah.
The bigger it gets, the more likely it is to fall apart.
Yeah, that's a good analogy. Another challenge is developing quantum algorithms. We need algorithms that are specifically designed to take advantage of quantum computers. It's not just about running old algorithms on faster hardware. We need totally new ways of thinking about computation.
It sounds like we need a whole new generation of quantum programmers and algorithm designers to really unlock the power of these machines.
Absolutely. And we also need to make quantum computing more accessible. Right now, it's a very specialized field. You need expensive equipment and a lot of expertise. So we need to develop more user-friendly interfaces and tools to make quantum computing available to a wider range of researchers and developers.
It's like the early days of the internet when only a few people could use it. We need to democratize quantum computing to really see its full potential. But these challenges also create some incredible opportunities, right? What advice would you give to someone who's interested in a career in quantum computing?
It's a fantastic field to get into right now. There's so much to discover and explore. I would say dive in and learn as much as you can. Build a solid foundation in math, physics, and computer science. And stay curious. Things are changing so quickly in this field, so be ready to always be learning and adapting.
It's clear that we're just at the start of the quantum computing revolution. What final thoughts would you leave our listeners with as they think about this exciting and unknown territory?
I think we're on the verge of a technological revolution that could completely change our world in ways we can't even imagine. Quantum computing isn't science fiction anymore. It's becoming a reality. So stay informed, stay engaged, and let your imagination run wild. The future is quantum, and it's full of possibilities.
This has been an incredibly deep dive into the world of quantum computing. We've talked about the fundamental principles, the groundbreaking new chips Willow and Majorana, and explored all the potential applications and challenges ahead. A big thank you to our expert for sharing their insights and knowledge with us. For our listeners, we'll be sure to include links in the show notes so you can learn more about Google's Willow, Microsoft's Majorana, and the fascinating field of quantum computing. Until next time, keep exploring and stay curious about the world around you.